Good morning, everybody. So we will soon start our first lecture. Let me have a brief introduction to our first speaker. Our first speaker is Professor Schlomo Razamat from Technion. He got his PhD in 2007 from Technion, and then he became a postdoc at Stony Brook. Also, that's where Schlomo and I met, and we collaborate for very long years. And then he became a member at the IAS Princeton. After Princeton, he went to Rutgers for 1 year. Then he became a professor back at Technion. And now he is a junior visiting professor at IAS as well. Professor Razamat's main research interest is in quantum field theory, especially understanding non-productive exact statement about quantum field theory in various space-time dimensions. And he also had a lot of influential works on quantum field theory and also duality among quantum field theories. So he will give us lectures on supersymmetric field theories. Yes, Schlomo, please.
Okay, thank you very much, Manbin, for the introduction. Let me try to share my screen.
Oh, by the way, Schlomo, what's your question policy?
Whatever is your question policy, that will be my question policy. I would
so
encourage questions.
Do you allow students to ask questions during your talk?
Yeah, sure.
Okay.
Yes, yes. I think it will be best, like, if somebody has a question, just to ask it. I hope. It is usually hard to follow the chat, so or when if you will see somebody raising a hand, maybe you can just give them.
Yeah, sure. Okay, so I will monitor the chat and the raising hands, and also if you have any question, please feel free to unmute yourself and ask the question.
So, do you see the screen?
Yes, I see.
Okay. So thank you very much for inviting me to this school. It's a great pleasure to be here, and I really regret it's not in China. And I hope we'll have many opportunities to meet in the near future in person. So let me start my 4 lectures. The topic of the lectures will be 4D supersymmetric dynamics and geometry. And first, I will start from some kind of a simple introduction, or what is the motivation for what I'm going to tell you and what we are going to discuss. So I will draw this diagram that probably many of you have seen many times by now. So we will be discussing quantum field theories, specifically in 4 dimensions, but let me be a little more general now and not specify the dimensions. So a way to think about dynamics of quantum field theory is to define certain quantum field theory or conformal field theory in the UV, which I will call here CFT UV, and then deform it with some deformation. Okay, and we will discuss what are these deformations. And then this defines an RG flow, a normalization group flow, to another fixed point in the infrared. Okay, so this fixed point in the infrared can be many things. It can be a gapped theory. Okay, there might be no degrees of freedom left in the infrared. It might be describable by free fields. Okay, for example, free vectors. Free vectors or free matter fields, or it can be an interacting SCFT. Okay, there are many possibilities. And the question we want to address, or main question we want to address, is given the CFT in the UV, and the the deformation delta, how can we determine what happens in the IR? Okay. So why is this question complicated, or why is it interesting? Okay. So this question is complicated and interesting because typically, or in many situations, what happens during the RG flow is that we undergo some region of strong coupling dynamics. Okay? So we start from some theory we understand, and then we turn on some deformation, and then these deformations grow, and then perturbation theory breaks down during the RG flow. We cannot trust perturbation theory, and typically it's very hard to access the very deep infrared using perturbative techniques. Okay, so this is a hard problem. So how do you solve a hard problem? Well, there are many approaches. Okay, so let me list some approaches that have been used to discuss non-perturbative or strong coupling dynamics in quantum field theory. Okay, so let me start from things I will not discuss here. Okay, so one such approach is to look at the endpoints of the flow. Okay, so at the endpoints of the flow, we have these theories with CFT UV and CFT in the IR, which enjoy some symmetry, some special symmetry, in particular, in some cases, conformal symmetry. And we can try to use this symmetry to fully understand, for example, the theories at these endpoints without use of perturbation theory. Okay, this is the program which is very popular in recent years, and it goes under the name of Bootstrap. So fix as much as we can about these quantum field theories or conformal quantum field theories by using symmetries alone. Of course, there are other approaches. For example, we don't have to go to the endpoints of the flows. We can consider some simplifying limits. And of course, all of you know that in last 20 or 30, 25 years, many such limits were studied. For example, large N limit, where you can relate problems of strong dynamics in quantum field theory to gravity, to simpler problems in gravity. More recently, people are studying other limits, such as looking on some properties of operators with large charges in a given quantum field theory, and so on. And finally, the approach that will be useful for us in these lectures is supersymmetry. Okay. So that's what we will do in these lectures. That is one thing that we will do in these lectures. We will not study the most general such setup. We'll study such a setup in the context of supersymmetric quantum field theories. And the reason we will do that, and that we will see already today, is that in this setup, we have a lot of very powerful non-perturbative techniques, which will allow us to say something about such very complicated problems. And in many senses, the supersymmetric quantum field theories are to non-supersymmetric quantum field theories as complex functions or complex analysis, okay, is to real analysis. Okay. So there are many things that we can say about supersymmetric theories, which are much harder to say about non-supersymmetric theories. And it is due to certain meromorphic or holomorphic properties of these supersymmetric theories, and we will encounter some of them here. Okay, so this is one thing. Second thing that we will do is we will embed this type of a flow between UV and the IR, okay, in a bigger setup. Okay, this will be another thing we will do. So again, we will discuss supersymmetric theories, and to be concrete, we will mostly focus on minimally supersymmetric n=1 quantum field theories in 4 dimensions and study such flows and try to understand them. And then the next thing we will do, or the other thing we will do, we will embed this thing into a bigger setup. Okay, instead of looking of these theories directly in 4 dimensions, we will embed these things in quantum field theories in D, which is bigger than 4. Okay? So we will add new degrees of freedom. And this fact that we will add new degrees of freedom will allow us certain tools or certain understandings about the dynamics of theories directly in 4 dimensions, which is hard. These techniques and these tools are not are hard to understand, or these effects that we will discuss are hard to understand if you restrict yourself to 4-dimensional physics. And this embedding has a bigger generalization, of course, into string and M theory. Okay, so we will not discuss this embedding in string theories and M theory in my lectures, but this is what Sakura Schaffer-Nameki will do in her talks. Okay, so our talks are philosophically related in this respect, that we want to understand quantum field theories, dynamics of quantum field theories in lower dimensions by embedding them in bigger setup. So in my lectures, I will focus on quantum field theoretic tools, and Sakura will discuss other types of tools, which also come from string and M theory. Okay, so if you wish, let me draw a very philosophical picture. So this is the space of quantum field theories in 4 dimensions. And these dots represent various theories. And for example, we want to understand the relations between different theories. And you can view this space of theories in some kind of landscape with mountains and valleys and whatnot. And if you look on non-supersymmetric theories, this is covered in some kind of fog, and there are a lot of clouds, and it's very hard to see far ahead. So the supersymmetric domain is where we have, in a sense, less clouds and less fog. And what we are going to do, we are going to have a bird's eye view of this supersymmetric domain. Okay, we will try to understand, from kind of above, losing certain details of this 4-dimensional dynamics, how this space of theories looks like. Okay, and again, in this way of thinking, we will lose certain, understandings of how these quantum field theories work directly in 4 dimensions. What are the what is actually happening in 4 dimensions on one hand, but on the other hand, we will see much more clearly, in a clearer way, how things are related. Okay, how very interesting strong coupling dynamics emerges from this picture. Okay, so in a sense, the main goal of what we will do will be geometrization of strong dynamics in 4D. Okay, and we will see in great detail what it means and what it gives us, what we can achieve with this approach. Okay, so this is very philosophical introduction, and let me, before starting the actual lectures, give an overview, a plan of the lectures. So what will be our plan? Okay, so we will have 4 lectures. So today I will start by discussing the basic supersymmetric toolkit. Okay, so I mentioned that supersymmetry is very powerful. You have a lot of tools. So today I will just give you a list of tools that you can use to address the complicated problems in QFT that we want to address. I stress that we will be in 4 dimensions. Okay, many things that I will say can be generalized to other dimensions, but I will focus on 4 dimensions, and I will focus on minimally supersymmetric quantum field theories, so n=1 quantum field theories. Okay. There are many more tools that we have at our disposal if we allow more supersymmetry, but we will only discuss minimally supersymmetric quantum field theories. Okay. And what we will do today in this lecture 1, again, will be a list of tools. I will explain where these tools come from. I will not derive them in detail. There are some more details in the lecture notes that I have sent you. I will say a couple of words about them, and in the references in those lecture notes. It will be some kind of hitchhiker's guide to supersymmetry, if you wish. Okay. Then in lecture 2, we will discuss dynamics. Okay. Still directly in 4 dimensions. And what we will discuss is IR dualities, emergence of symmetry, and conformal dualities. Okay. So this will be completely 4-dimensional and supersymmetric discussion. And then in lectures 3 and 4, okay, we will discuss the geometrization of this picture. The geometry will appear. In particular, certain aspects of the dynamics that we will discuss in lecture 2, we will have a geometric interpretation, and we will see how this whole program works. Okay. The last thing I want to say is about the notes. So I typed some notes for this lecture. So I have sent you the lecture notes for lecture 1 and 2 already. So these lecture notes contain more details than I will be able to present in the lectures themselves. Of course, much more details can be found in references. And again, I will not mention practically any references during the talk. So all the references are in these lecture notes. And also these lecture notes contain some exercises. So of course, if you really want to understand the material, you should try to do the exercises. Some of them are trivial. Some of them are less trivial. And I don't know, either in the end, at the end of the school, or every 2 days, like after first 2 lectures, and in the end, I will also give at least some solutions to some of the exercises. So this is the plan. So are there any questions about the introduction and the plan? Okay.
So I have a question about this and RG flow.
Yes.
So although you said in the 4D, but I wonder that in general, that these 2 safety, at least UV and IR, and do they have 2 in the same dimension?
You mean whether I will start and end my RG flow in the same dimension?
Yes.
Excellent question. No. So that will be the part of the geometrization picture. Okay. So in this lecture today and tomorrow, we will be in the same dimension, and it will be 4. But in the following lectures, the other 2 lectures, we will actually start our RG flow in higher dimension. That's exactly what we will do. And then we will flow to 4 dimensions. And of course, you can generalize this picture to flowing between other dimensions, but we will be interested in physics in 4 dimensions, but we will allow starting the RG flow from higher dimensions eventually. Okay. So if there are no more questions, let me start discussing the toolkit. Okay, what kind of tools do we have with which we can analyze quantum field theories in 4 dimensions? So again, I stress that we will be in 4 dimensions unless I will say otherwise. And we will start with understanding what...
Schlomo?
Yes.
There's another question in the chat saying, is it possible to go from UV to a higher dimension in IR?
There are constructions where you can start from lower dimensional quantum field theories and try to construct higher dimensional theories, but this is not an RG flow. For example, one of these constructions goes under the name of deconstruction, where you have a quantum field theories. You see, the problem is that when you go to higher dimensions, typically the problem is that you need to kind of get more degrees of freedom, okay? In the RG flow, you intuitively lose degrees of freedom. So if you want to go to higher dimensions, you need to add degrees of freedom. So there are certain constructions in lower dimensions of quantum field theories where you take the limit of these quantum field theories to be big, like you have a quantum field theory with a lot of matter, and you take the amount of this matter to be big. And then there are certain claims that in certain cases, in this way, you can construct quantum field theories in higher dimensions. That's one thing. Another thing is that we will discuss it in detail in lectures 3 and on, is that sometimes you can have a lower dimensional quantum field theory, which is actually UV completed by a higher dimensional theory. But that we will discuss in lecture 3. Does this answer the question? Okay. Okay, so let me start discussing the non-supersymmetric tools that we have to address our question. And the first thing we will consider is, of course, symmetry. What can we say about the symmetry in these RG flows? So again, we start from CFT in the UV. So we have our starting point in the UV and the end point in the IR. We start from some CFT and we add certain deformation that very abstractly I denote by delta. And this deformation breaks the conformal symmetry, introduces a scale, and we start flowing. So one thing that we have here in our starting point is certain global symmetry, which we'll denote by GUV. Okay. So this GUV is the global symmetry that is preserved by the CFT and by the deformation. Okay. So it's not just the symmetry of the UV point, is what actually also the deformation which starts the flow preserves. Okay? And we assume that this deformation doesn't, this symmetry GUV is after we have taken into account any possible issues with spontaneous symmetry breaking and so on. So this is the real symmetry that we have during the RG flow. And then we can ask, what is the symmetry in deep infrared? Okay, we flow to the very, very low energy, and we want to ask what can happen in the infrared. So there are several things that can happen. Okay, so the symmetry in the infrared can be bigger than GUV. Okay, okay, so this GIR can be bigger than GUV. How this can happen? This goes under the name of emergence of symmetry. Okay. Very intuitively, you have some degrees of freedom in the UV, which transform in some representations of your symmetry, and some of these degrees of freedom might be gapped as once you get into the infrared, and the actual symmetry of your theory might be bigger than you started with. Okay, this is something maybe you don't always think about, but this can happen in the flow. So the symmetry in the infrared might be bigger than the symmetry in the UV. On the other hand, although we defined our GUV to be the symmetry which is preserved in the RG flow, so it is not broken during the RG flow, we expect to get at least GUV in the infrared. The symmetry can be actually smaller. Okay, and why it can be smaller? It can be smaller in a trivial way. Okay, it can be smaller because it's not acting faithfully on the degrees of freedom of the infrared theory. Okay, so in a sense, we didn't break the symmetry, but there is nothing which is transforms under that symmetry. Okay, for example, if the theory is gapped, if there is nothing in the infrared, we could have had a symmetry in the UV, but we didn't break it, but just there is nothing which transforms under that symmetry. Okay, so just by looking at symmetries, it seems not much that we can say. Okay. However, of course, there is a caveat, and of course we can say something, and this something is called anomalies. Okay. And again, anomalies is a tool that exists there, whether we have supersymmetry or don't have supersymmetry. So what are anomalies? So say we have some global symmetry G, and we compute a partition function or generating function or effective action, and we turn on some background fields A, which couple to the conserved currents of this global symmetry. And we asked ourselves, what happens if we introduce certain gauge transformation for these background gauge fields? So these are not dynamical gauge fields. These are background gauge fields. And then we compute this partition function with respect to these new gauge fields, which we transformed with this gauge transformation. And there is a question whether the result is the same as the one we started with or whether it is different. Okay? If it's different, we say that we have an anomaly, a 't Hooft anomaly. Okay? So the point is that the failure of this equality is quantifiable. Okay, and the main kind of thing about these 't Hooft anomalies, like the main intuition about these 't Hooft anomalies, that this kind of failure of the equality is an obstruction to gauging the symmetry. So here in this logic, explicitly, I assume that my group G is the usual symmetry, okay? And it's a continuous symmetry. But all these statements that I'm going to say have a generalization to discrete symmetries and to symmetries which are so-called higher form symmetries, okay? For which the gauge transformation is not a zero form. It's not just a scalar function, but it is a higher form, and this these types of considerations got a lot of attention in last years, in recent years. I will not discuss this here, but this is again this generalization to higher form symmetries and to discrete symmetries is certainly part of the toolbox that we need to consider. So how is this anomaly quantifiable? And of course, you all have learned about anomalies, and there are various things, various ways how to understand anomalies. For example, if you have a chiral anomaly, it is captured by certain triangular Feynman diagrams. Again, I'm in 4 dimensions, and it is captured by certain coefficients, which can be written in the following way. Schematically, if we have a weakly coupled theory, for example, and we want to compute certain 't Hooft anomaly, obstruction in gauging certain symmetry, or in this way of phrasing things, in understanding how things transform, we can compute trace over all the chiral fermions in our theory and compute this type of a coefficient. And this measures for us this obstruction, like the way there is the failure of this equality is captured by certain factors which depend on these types of numbers. And of course, you know very well how this happens. Say if you have a U1 symmetry that you want to gauge, you need, for example, to compute this cubic anomaly and sum over all the charges of all the fermions, of all the chiral fermions. And if this number is not equal to 0, you have an anomalous symmetry and you cannot gauge it, and so on. Now, what I want to mention here is that there is a nice way to package these anomalies, these 't Hooft anomalies, in something which is called anomaly polynomial. Okay. Again, I don't teach you what these anomalies are and anomaly polynomial. I assume you seen this somewhere else. If you did not see this anywhere else, I encourage you to look at the notes. There are a little bit more details, and look at the references. So the main point is that these anomalies, these 't Hooft anomalies in 4 dimensions, can be packaged in something called an anomaly polynomial, which in 4 dimensions is a polynomial of 6 forms. Okay, it's a polynomial. It's a formal polynomial in characteristic classes. Of characteristic classes corresponding to various symmetries that you might have. Okay. For example, if you have this anomaly polynomial in 4 dimension, again, which is a 6 form, then an anomaly that I will have written on the previous slide will be packaged in this polynomial as in the following way. There will be these numbers, and in our normalization, there will be 1/6, and there will be a combination of characteristic classes corresponding. These FIs correspond to these 3 groups, G1, G2, and G3, and so on. And we will encounter examples in more detail in what follows. Now, importantly, what will be important to us is that this anomaly polynomial, I for D, is RG invariant. Okay. There are various arguments to why is it so. So let me mention here one argument, and probably we will see another argument later on. So this argument is due to 't Hooft, okay, the so-called 't Hooft anomaly matching condition. It's not the best or modern argument, but it's very intuitive. So the argument is very simple. Say you have certain anomaly, you cannot gauge some symmetry. So you just add certain fermions to your system such that the anomaly now will be 0. You weakly gauge your symmetry, you flow into the infrared, and then you decouple the fermions that you have added. Okay? Since everything is consistent in the flow and you can tune this gauging, this coupling to be very, very small, you can decouple these fermions in the end. And then, since you know what was in the beginning and what you added, and then the total anomaly was 0, in the end, again, you assume that you can decouple the same fermions, and you can compute the anomaly of what has remained, and the total anomaly has to be 0. The anomaly should not have changed. Okay, and there are other arguments, anomaly inflow, and so on, that we will mention a little bit later. Okay. So why is it important? So it is important because now we want to understand this flow between UV and infrared. We have now a certain invariant of the flow. We know something about what will happen in the infrared by knowing something about the UV. Okay. So what we know is that, say, we compute these 't Hooft anomalies and, say, package them in this anomaly polynomial in the UV, and then we compute this anomaly polynomial in the infrared, we need to get the same result. Okay, where here I assume that we compute this anomaly polynomial with characteristic classes for the symmetries that we can identify in the UV. I mentioned that there can be emergent symmetries in the infrared. Okay, there can be more symmetry in the infrared. So for those symmetries, I will not be able to introduce them in the UV. I cannot compute this anomaly polynomial in the UV. So when I only restrict my computation in the infrared to the symmetries that I can identify in the UV, this equality should hold. So only use symmetries visible in the UV. Okay? So this is a very strong statement. This is something that if we claim that we understand how dynamics in the infrared happens, we can check this equality. And if this equality doesn't hold, our statement is just wrong. Okay? How this, the fact that symmetries might not act in the infrared or not act faithfully in the infrared, how does it come into this discussion? Well, if a symmetry doesn't act faithfully in the infrared, if there is nothing charged or nothing transforming under certain subgroup of the symmetry, that will mean that a certain part of this anomaly polynomial is 0, is just vanishing, because there is nothing transforming under this symmetry. So not acting faithfully translates that at least some part of this anomaly polynomial is equal to 0. But that means that those anomalies also had to be 0 in the UV. Okay? So if there is a symmetry which is not acting faithfully in the infrared, it had to be that the corresponding anomaly was 0 in the UV. Okay, so you see that these anomaly polynomials, or 't Hooft anomalies in more general, can tell us something about the dynamics. And we will use these anomalies to infer certain statements about physics in the infrared. Okay. Now, these statements about the anomalies are not just true for RG flows, they're also true for other deformations. For other continuous deformations of the theories. For example, the ones which preserve conformality. Okay, so here I have the discussion where I break conformal symmetry and start flowing, but there are other deformations that we will discuss momentarily, which are usually called exactly marginal deformations. When you don't break conformality, your theory, your CFT, has a certain parameter which you can continuously change without initiating a flow. So the fact that the anomalies don't change is true by the same types of arguments also in these situations. Any questions about Hooft anomalies?
So may I ask a question? Whether that's true for the anomaly is still well defined if the symmetry is spontaneously breaking?
So if the let me ask you the question and tell me if I understood it correctly. You're asking what goes wrong if the symmetry is spontaneously broken?
Yeah, maybe the question is that if the symmetry is spontaneously broken, whether we are still able to define true for the anomaly or not.
The symmetry is not there. You have broken it. I have nothing to compute.
No, I mean spontaneously symmetry breaking, not really.
Sure, but the symmetry is not there, right? You have this, as you know, when symmetry is spontaneously broken, there are many things that you can say, but you know, it is not there. The symmetry is not there. So if you wish, you chosen a vacuum which broken the symmetry, and you flow to some setup which doesn't have that symmetry in the infrared.
I see. Thank you.
Okay. So till now, the discussion was non-supersymmetric. So now let us add supersymmetry. Okay. And discuss what kind of tools we have when we add supersymmetry. Okay. So we are in 4D with minimal supersymmetry. And first, let's start with the starting points of these RG flows, where we have the superconformal symmetry. Okay, so the fact that we have a superconformal symmetry, that means that we have certain group of transformations. So we have the supercharges, the superconformal charges, the translation, the spatial conformal transformations, and of course we have the complex conjugates of these guys. We have the scaling transformation, the dilatation delta, and most importantly, we have something which is called the R symmetry. Okay, the R symmetry is certain abelian symmetry under which the various supercharges are charged. Okay, it's just a U1 global symmetry. Again, we are here in the as n equal 1 4-dimensional minimally supersymmetric case. So it is an n equal 1 symmetry, sorry, a U1 symmetry, which always has to be there. It is part of the superconformal group. And much of the magic of supersymmetry relies on this R symmetry, as we will see now. Stems from R. Okay. So again, R symmetry is something under which the supercharges and the superconformal charges are charged. It has to be, it is part of the superconformal group. It is there. It is the symmetry under which different fields in the supersymmetric multiplets have different charges. It's a very interesting symmetry, and we will see how this symmetry gives us a lot of special tools which only exist for supersymmetric theories beyond the 't Hooft anomalies that we have discussed, although the relation to 't Hooft anomalies will be very intimate. So let me start by listing these various powers that our symmetry has. What can it give us? What can it give us? Well, there are certain things that you can compute. For example, some things which go under the name of conformal anomalies. So you can take your favorite conformal theory. Again, this you can do without any supersymmetry, and put it on a curved background and compute the trace of the stress energy tensor. So T mu nu is the stress tensor, stress energy tensor. And typically, this type of expectation value of the trace of the stress energy tensor will have two terms. Okay? One comes with a coefficient which is called A, and another comes with a coefficient which is called C, where E4 is the Euler density, and this is the square of the Wild tensor. Okay, the details are not very important, but it's very important that there are two numbers which are associated to any CFT, which are called the A and the C anomaly. Without supersymmetry, not much is known about these numbers. You know, what happens to these numbers when you flow. There is one thing which is known. It's as was conjectured by Cardy and proven by Komorgotsky and Schwimmer recently. There is certain inequality that these, for example, coefficients A have to satisfy. That A in the AR has to be less than A in the UV. But beyond that, it's very hard to understand how these numbers are related between the flows. However, with supersymmetry, there is certain things that we can say. So first of all, there is an intimate relation between this R symmetry and these numbers, C and A. So let me write it down. This was discovered by Anselmi, Friedman, and Grisaro, I think, about 25 years ago. And in supersymmetric field theories, these numbers A and C, although they look to come from completely different source than R symmetry, are actually related to R symmetry. So A and C anomalies are always given by this expression. So A is equal to 9/32 trace of R cubed, so a cubic 't Hooft anomaly of this R symmetry, minus 3/32 trace of R, and C is equal to 9/32 trace R cubed, minus 5/32 trace of R. Okay, and the reason why this happens is that as we have written here, the R symmetry current is part of the superconformal algebra, and in the superconformal algebra, also this is the algebra which involves also space-time symmetries, in particular stress energy tensor. Various properties of stress energy tensor are related by this big structure of the algebra to properties of the R symmetry. And by exploiting these relations, this supersymmetric algebra and what it implies about the trace of stress energy tensor, you can derive these types of relations. That these types of anomalies are related to 't Hooft anomalies of the R symmetry. Okay, where here the R symmetry which is used, which will be very important and we will discuss it soon, is the R symmetry which appears in the superconformal algebra. Okay, so this is one thing, and then you can ask, how does this help us to understand what these anomalies in the IR are? Okay, and the reason we can understand these anomalies in the infrared is again stemming from the fact that we have this bigger superconformal algebra in which the R symmetry currents live in. Okay, so we start in UV and we have certain R symmetry, RUV. We initiate a flow and we flow to a different theory in the infrared. And in the infrared, say we flow again to some superconformal theory, and it has different R symmetry in the infrared. And what we do, we introduce a deformation in these talks. Okay, sorry. So we introduce a deformation delta, as I have written before, and we will always assume that the deformation that we have introduced preserves supersymmetry and preserves R symmetry. Okay, so this deformation breaks conformal symmetry, so we don't have to have R symmetry during the flow. Okay, R symmetry is part of the superconformal group, but the deformations that we will introduce preserve some R symmetry. Okay, and that R symmetry will be some combination of the R symmetry in the UV and the other symmetries that the theory in the UV might have. And soon we will write it down. And then the question is, can we, by knowing this R symmetry in the UV and other symmetries which are preserved by this deformation, can from this information deduce what will be the R symmetry in the infrared? If we know that, as we have seen on the previous page, we can also say what the A and C anomalies are. Okay. So under a certain assumption, and the assumption is that there are no emergent abelian symmetries in the infrared, or at least that they have certain properties that I will now say, we can say the following thing. So first of all, what can be the R symmetry in the infrared as a function of this R symmetry in the UV? Okay. So we are interested in understanding what the R symmetry in the infrared is. And the statement is that it can be the symmetry in the UV plus certain combination of symmetries, of abelian symmetries, which are preserved during the flow. So here, if you wish, it's schematic encoding of the charges of this new R symmetry in the infrared. The R charges in the infrared are given by the R charges in the UV, plus some combination of charges under various abelian symmetries that we have. And the goal is to determine these alpha i's. So when this can fail if there are certain abelian symmetries that appear in the infrared that we cannot see in the UV. Okay, we are trying to determine this guy starting from the UV. So we might fail in doing so if there are certain abelian symmetries in the infrared which emerge and then can mix in this sense with the R symmetry. Okay. So now, again, we use the same supersymmetric magic related to the fact that R symmetry is part of the superconformal group. And this was done by Intelligator and Wecht about 20 years ago. And this procedure goes under the name of A maximization. Okay. And what we can say is the following: just by analyzing the various implications that superconformal symmetry implies for various 't Hooft anomalies, you can derive that, for example, for any global symmetry that you have, the trace U1 anomaly should be 9 times trace U1 times R squared anomaly for any U1. Okay, this is one thing that you can deduce. And another thing that you can deduce is that trace U1 squared anomaly, U1 squared times R anomaly should be less than 0. And this follows from some positivity relation of some 2-point function of the currents. Okay. And from these two statements, you can derive that if you define a trial anomaly, and I denote it by A alpha here, which is 9/32 trace of R of alpha cubed minus 3/32 trace of R of alpha, where R of alpha is this type of a combination. We define R of alpha starting from our RUV and then mixing it with all the other abelian symmetries that we can have. So we just compute this type of anomalies, which will be a combination of various 't Hooft anomalies of R symmetry and all the abelian symmetries that we have in our system. So computing these trial anomalies and finding a maximum of this function gives us the alpha I, which give us the superconformal R symmetry in the infrared. Okay, so the derivation is very simple. It is in the notes. I will not do it here to save time. But again, the magic is that, again, superconformal symmetry relates various 't Hooft anomalies. And by these simple statements, we can derive this powerful argument. And again, this argument has a caveat that we need to have all the possible U1s identified in the infrared. If we have emergent U1s, this argument can fail. But if we don't have these emergent U1s, this is a procedure. Any questions?
Maybe I may ask a question. So when you read the trace of R or trace of R squared, this trace take over which space? It trace over
Okay.
all of the state or trace over what? All of the fields or what?
It's a notation to compute these anomalies. And this trace, if you have a Lagrangian description in terms of fields, and in these talks we will always have a description in terms of fields, this trace is over all the chiral fermions in your theory. So you just sum over all the representations, all the charges of your chiral fermions, and compute these anomalies. Like in several minutes, we will have an example. Is it clear?
I will wait a moment later, maybe.
Okay. Any additional questions?
So for
right. Does the index I run over abelian factors in GUV, in the UV global symmetry?
You can do that, but it's a good exercise to show that these, so you say you have some big group, GUV. Yeah. It has some non-abelian parts and some abelian parts. You can look on the maximal torus and define it for maximal torus. It's a good exercise to convince yourself that if these U1s are some cartons of non-abelian factors, they will, if you do the same maximization, these coefficients will always turn out to be 0.
Okay.
Okay. So only abelian symmetries can contribute.
I see.
Okay, but it's easy to prove. So I really encourage you to do that exercise.
Okay, thank you.
So
yes.
for 4D n equal 2 theory, can we use the same technique to compute A or C central charge?
Of course. Everything I say will hold for n equal 2 also. The other way around, of course, doesn't work. Many statements that you know about n equal 2 might not hold for n equal 1. But everything I am telling you works for n equal 2 as well, and n equals 3 and n equals 4.
Okay, thank you.
So using these relations between R symmetries, R symmetry charges and A and C anomalies, you can compute various things. For example, let me mention something that we will use later on. If you have, say, a free field, free chiral field, okay, you can compute these anomalies. A free chiral field, like if you have a chiral multiplet contains a certain scalar and a certain fermion, the scalar is a free field, so it has dimension 1. And you can ask what is its R charge, and again, by using the superconformal algebra and various unitarity bounds, in general, for chiral fields, there is a relation between the dimension of a chiral field and its R charge, and it goes like that the dimension is related to a chiral field. Dimension is 3/2 the R charge, and for free field in particular, as the dimension is equal to 1, the R charge is equal to 2/3. Okay, so you can use this fact, for example, to compute the A and C anomalies of a free chiral field, and I will denote them by A chi and C chi, and these turn out to be 1/48 and 1/24. In the same way, you can compute these anomalies for free vector fields, and they will turn out to be 3/16 and 1/8. Okay, and as an exercise, and that appears in the notes, I want you to verify the following simple fact. Say you have a theory such that the free assignment of R charges, basically 2/3 to all the chiral fields that build this theory, is a valid assignment. It's consistent with all the superpotentials. It is anomaly free and so on. Then if this happens, then this assignment of R charges is necessarily the superconformal one. Basically, that assignment of charges always solves this A maximization procedure. Okay, so free assignment of R charges, if it is legal, always solves a maximization. Okay, this will be important for what we'll do in the following. Okay, so it might be that the free assignment of our charges is anomalous, for example. It's not consistent with gauging symmetries, or it's not consistent with superpotentials. But if it is consistent, then this holds. And this is a good, nice exercise to get a feeling of this A maximization procedure. Okay, so we discussed several things: the 't Hooft anomalies for non-SUSY theories, the expression of A and C in terms of 't Hooft anomalies of R symmetry, and the A maximization. So now let us discuss some more interesting things. And these more interesting things are deformations. So till now, I did not discuss at all what are these deformations. Delta, you know, I have too many things which are called delta, so let me specify CFT UV plus delta that we have discussed. So what are these deltas that I want to add? Okay. So there are several interesting deformations that supersymmetric quantum field theories can have. And again, I will only concentrate on deformations which preserve supersymmetry and preserve R symmetry. Okay, so there are deformations which are called superpotential deformations. And in these deformations, okay, superpotential W, we add a term into the action, which has the following form. We have a coupling, which I will denote by lambda O. And then we have the term in the action, which looks like the integral over space and the integral over half superspace. And we integrate over a chiral operator in the theory. Okay. And again, chiral operator, as I mentioned, has this property that the dimension of the operator is equal to 3/2 the R charge. And then we can ask questions whether this deformation is interesting or not. So if the deformation, this R of O, is less than 2, then this deformation is what is called relevant. So if you wish, lambda O has positive mass dimension. And you can convince yourself about that, again, by looking at this relation between the R charge and the scaling dimension. If the R charge is bigger than 2, this deformation is irrelevant. That means if we flow into the infrared, this deformation becomes smaller and smaller. So basically, we don't leave our CFT in the UV. If we turn on an irrelevant deformation, the theory in the infrared is the same theory we started with. Here, we might flow to a different theory. If the RO, the R charge of the operator O is 2, this operator is marginal. Okay? And then we don't know whether it is marginally relevant, marginally irrelevant, or exactly marginal if we don't flow. And what actually happens, we will discuss in a couple of minutes. Okay? Another type of deformation that we can have is given a CFT with some global symmetry G, we can gauge a subgroup of that symmetry. So we can gauge a G inside the symmetry that we have in the UV, in the CFT. And by gauging, again, we can phrase it by coupling our theory to dynamical gauge fields and turning on certain superpotential, which has this form, W alpha, where W alpha is a certain chiral superfield again, which as its lowest component, it has the gaugino, and then in the multiplet, we have also the field strength of the gauge field encoded. So if you write this term in components, you will get the usual Yang-Mills term and kinetic terms for various other fields that you have here. And the coupling tau of G is given by, say, 4 pi I over G squared plus theta over 2 pi, where theta is the theta angle. So having this deformation, this gauging of a symmetry, we can ask whether this gauging is, again, relevant, irrelevant, or marginal. And here again, the R symmetry comes into the game, and it helps us. So what about the beta function of the gauge of the coupling of, say, of the coupling G? So the statement is very simple. The beta function is proportional to minus a certain 't Hooft anomaly, trace of R G squared. Okay, this is a very important statement that we are going to make. So if you want to compute the one loop anomaly, a one loop beta function at your fixed point, you just need to compute this type of an anomaly and look at what is the result that you get. So if trace R G squared is positive, then you have a UV free gauging or asymptotically free gauging. That means if you flow into the infrared, you flow to strong dynamics. Okay, so this gauging is interesting. If this anomaly is smaller than 0, this 't Hooft anomaly, your gauging is IR free. So in the infrared, the gauge coupling becomes smaller and smaller, and you have weakly coupled gauge field or free gauge fields floating around in the infrared. If trace R G squared is equal to 0, the gauging is marginal. And again, in the moment we will discuss how do we know whether it's exactly marginal, marginally relevant, or marginally irrelevant or marginally relevant. And again, the fact that 't Hooft anomalies enter here is related to the fact that the beta function is measured by the failure of conformal symmetry, and the R symmetries are part of this conformal symmetry. So you can relate various quantities, which involve this conformal symmetry to 't Hooft anomalies of R symmetry. As far as I know, this fact, at least I learned this fact from an old paper by Tachikawa and friends, I think Benini and Wecht, but it is probably known from before. And again, the citations are in the notes that I mentioned. So this will be a very important tool. One thing which is important about this tool is that it is completely non-perturbative. Okay, if you know how to compute these anomalies, whether your theory is weakly coupled or strongly coupled, it doesn't matter. These statements will hold. Any questions about this?
This is only one loop contribution, right?
Exactly. Very good. Yes. So this is the idea here is you have your theory, you have your global symmetry. Okay. You are at a fixed point and you want to turn on weakly gauge some subgroup of this global symmetry, and you want to understand how the one loop behaves, where you have asymptotically free, IR free, or marginal gauging, and that's what captures the this one loop behavior. If you know about NSVZ beta function, you can deduce the same result also from NSVZ beta function. Again, it is also in the notes if you will read them. Okay. Okay. So now another point which I left unanswered is what happens with these marginal couplings. How can we know whether a coupling is marginally relevant, or marginally relevant? And here there is a really beautiful result due to a paper by many people. I think it's Green, Komargotsky, Seiberg, Tachikawa, and Wecht from several years ago, and it goes back to a classic result by Lee and Strassler. And this is a rephrasing of this Lee and Strassler argument in much more group theoretic and a nice way. And the statement is very clear. Again, by exploring various relations or various facts that you can deduce using supersymmetry, you arrive at the following statements, very strong statements. So if you have a marginal deformation, it can be actually only exactly marginal or marginally irrelevant. It can never be marginally relevant. Okay, marginal deformations in supersymmetric theories are always either marginally relevant or exactly marginal. Okay, by exactly marginal, we mean that the beta function vanishes to all orders in perturbation theories and non-perturbative. Okay, and the only way for marginally for a coupling not to be exactly marginal is if the operator corresponding to this marginal deformation recombines with the conserved current. Okay, conserved currents and superpotential deformations and are related to something which is called short multiplets. We'll say a little bit more about it later on. And the only way for a marginal operator to become irrelevant, marginally irrelevant, is to recombine with the conserved current. And the next statement, which will be extremely powerful, is how we actually determine what can recombine with conserved currents and how can we determine this, what are the exactly marginal deformations. So what we define something which is called the conformal manifold. Okay, and conformal manifold is just the space of exactly marginal couplings. So we have a lot of deformations that we can turn on, a lot of couplings that we can turn on. We can think of them as spanning as certain complex space. This space, the space of only exactly marginal deformations, is called the conformal manifold. And say we're at a certain point, we have a certain CFT, and we want to find what are the exactly marginal deformations from that CFT. And the statement is that locally near that that CFT, the space of this the space of exactly marginal deformations is given by certain simple quotient. You take all the couplings that you have in your theory, all the marginal couplings that you can have. You look on the set of these couplings. You associate charges to this coupling under the global symmetries in the of the theory that you start with. So the way you associate your couplings is, again, you have a superpotential of the form lambda I OI. OI are operators which have certain charges. So you the couplings lambda I transform in the conjugate way. So you think of these couplings as transforming under the global symmetry of your theory. And then you compute the following quotient. You compute the quotient of the set of all the couplings that you have by the complexified global symmetry group of your fixed point. Okay, and this space will be the space of exactly marginal deformations. And if we will have time, we will perform one such computation today. Any questions about this general statement? Okay. One kind of immediate consequence of this statement is, for example, if you have a coupling which comes with an operator which is not charged under any global symmetry, that coupling is exactly marginal. Okay. Another simple lemma that you can immediately prove is if you have a Wess-Zumino model in 3 dimensions of cubic with cubic superpotential. As you know, there is this statement that this Wess-Zumino model always flows to infrared free fixed point. So this deformation is always marginally irrelevant. This follows immediately from this statement. So try to think why. And if you don't figure out, ask me later on. Now, before I give you an example of this type of a computation of the dimension of the conformal manifold or of conformal manifold itself, let me mention a couple of generic statements about flows, which typically are not appreciated by many people. So one statement is about something which is called dangerously irrelevant deformations. Okay. So here I made an analysis or told you whether deformations are relevant, marginal, or irrelevant. But these statements are tricky if you have more than one coupling. So let me give you an example. So say you have two deformations, and the coupling of first deformation is G1, the coupling of another is G2, and say the coupling G1 is irrelevant. That means if you start from this fixed point, okay, this is your CFT in the UV, you deform it by turning on G1, the RG flow will take you back to the CFT UV that you have started with. And say you have another deformation, G2, which is relevant. Schematically, again, if you turn on this deformation, you will flow to another fixed point. Okay. But now you can ask what happens if you turn on both of these deformations. Okay. So you turn on both G1 and G2. So what can happen is the following thing. So G1, by this perturbative analysis that we did, it will be expected to become smaller. G2 will be expected to become bigger because it's relevant. And then the question is, what happens near the fixed point? So there are a couple of possibilities. It might be that you will reach this fixed point, okay, the same fixed point, and then you think of this deformation, again, the deformation in this direction as irrelevant. Okay, it doesn't matter that you turned it on, you arrived at the same fixed point. But what also can happen is that when you go close to this fixed point, your perturbation theory breaks down. Because here this coupling G2 might be big, and the analysis which gave you the fact that this coupling is irrelevant doesn't hold anymore. Okay, and then what can happen is that you will flow to a different fixed point. Okay, and in other words, if you analyze this flow in steps, you first turn on this G2 coupling, and then you turn on this G1 coupling. This G1 coupling at this fixed point is actually a relevant deformation. It takes you to a new fixed point. And if such situations occur, this deformation G1 will be called a dangerously irrelevant deformation. Okay? Again, if you turn on both relevant and irrelevant deformations, the irrelevant deformations might actually become relevant in this sense. Is it clear? Any questions? Okay. There are other things that can happen if you have a relevant deformation or two relevant deformations. And again, if you flow with one relevant deformation to a fixed point, the other relevant deformation might become irrelevant at this fixed point. Okay. This is a somewhat less drastic effect, and so we'll not discuss it here in detail, but I want to stress it, this fact here, again, because you should not throw away certain deformations that you think are irrelevant if you are planning to turn on more than one deformation. So the way to analyze the dynamics of a flow in general is by turning on deformations one by one. Okay. If you want to turn on many deformations and you turn on all of them together and throw away some of them which you believe are irrelevant, you might be wrong in arriving at your conclusions exactly because of these interesting effects. Okay. How much more time do I have, Wendy? If the
So it's supposed to end like 11:30, but
okay.
you definitely don't have to talk all the. I mean, there should be some question sessions. So,
okay.
So you could just end at your convenience or at your planned point, and then we can have a question session.
Okay, so let me perform one computation, and then I will stop and we'll continue next time. Okay, so this was very abstract. So let me perform a computation, and I hope it will answer some of the questions that were asked till now. Okay. So an example that we will analyze is a very simple gauge theory. So let us take a gauge theory with an SUN gauge group, which is called usually an SUN SQCD, with an F equals 3n, where the number of flavors is equal to thrice the number of colors, the n. What does it mean? It means that we have chiral superfields in the fundamental representation, and we have 3n of them. And we have chiral fields in an anti-fundamental representation, and we also have 3n of them. Okay, we have various symmetries in the problem. So one symmetry is the SU3n rotating these fields. Another is SU3n rotating these fields. And we have also two U1 symmetries. One, a baryonic U1 symmetry, which gives charge +1 to these fields and -1 to these fields. And it is an anomalous symmetry. And there is another symmetry, which is anomalous, where you have you give charge 1 both Q and Q tilde. Okay, and now we want to understand what happens with this theory. What is the IR dynamics of this theory for general N? And here the analysis is very simple. Okay, so the only deformation we turn on is the gauge deformation. Okay, so we need to understand what happens with the beta function for this theory. Okay, so let us compute the beta function. And to compute the beta function, we compute the anomaly trace R G squared. And here is an example of computation of this anomaly to the question that I was asked before. What does this trace R G squared mean? Okay, so we simply sum over all the fermions that we have in this theory. So where do the fermions come from? So first of all, we have gauginos in this theory coming from the vector n equal 1 vector multiplets. Okay, so we need to compute this anomaly for the gauginos. Okay, so the R symmetry of the gauginos is always 1. Okay, so the trace the R of a gauginos is 1. And then we need to compute this trace over G squared. The gauginos are in the joint representation. So this trace over G squared gives us the quadratic Casimir of the joint representation, which is equal to n for SUN. Okay, so the gauginos contribute n. Okay, now we have the matter fields. Okay, so the matter fields, we start from the free theory. So the theory, these fields are free. So as we have discussed, the R charge is equal to 2/3. So the R charge of the superfields is equal to 2/3. These superfields contain a scalar field as a bottom component, and then they have also fermionic fields. But fermionic fields are related by supercharge to the bosonic field. So their R symmetry is not the same as the one of the bosonic field. It is shifted because we need to act with a supercharge. So if you do this computation, you get that the shift is by -1. Okay, so the supercharge of the fermions is 2/3. That's the R charge of this field Q and Q tilde minus a 1. Okay, and the fields are in the fundamental representation. So this quadratic Casimir is equal to 1/2. And then how many such fields we have? We have 3n fields in fundamental, 3n fields in anti-fundamental. So in total, we have 3n times 2. Okay, and this anomaly is equal to 0. Okay, so this means that since this 't Hooft anomaly is equal to 0, it means that the beta function of this gauging is 0. Okay, so this gauging is marginal. Okay, so now you want to understand what is actually the conformal manifold of this theory. Is this deformation exactly marginal or marginally irrelevant? Okay, here we have only one coupling. So this is the question we ask. So first, let us look at generic n. Okay, for generic n, I will mean n which is not equal to 3. We will see that something special happens for n equals to 3. Okay, so what is this conformal manifold? So for n which is not equal to 3, the only marginal deformation that this theory has is the gauge coupling. Okay, you cannot build any gauge invariant operator with R charge 2 that you can add to this theory. Okay, So this conformal manifold is computed by the quotient of this gauge coupling, G, or rather e to the 2 pi I tau, as we will now discuss. And we will need to quotient by this complexified global symmetry group. What is this global symmetry group at the after the gauging? It is SU3n times SU3n times U1 baryon and times U1 anomalous. So why do we need to use U1 anomalous symmetry? This is an important thing here. In principle, U1, the anomalous symmetry is not the symmetry after we perform the gauging. And why is it not a symmetry? It's not a symmetry because one way to think about it is because when you perform this anomalous transformation, it changes the theta angle. Okay. What does it mean that it changes the theta angle? It means that this coupling transforms under the anomalous transformation. Okay. So to perform this quotient, we need to quotient by all the symmetry. The SU3n, which rotates the fundamentals, SU3n, which rotates the anti-fundamentals, U1 baryon, and U1 axial, okay, the anomalous one. What is this quotient? Okay, what is it equal to? What does this coupling, the gauge coupling, transform under? It doesn't transform under SU3n. It doesn't transform under this symmetry and not under this symmetry. Well, one way to say this is because these symmetries are not anomalous, but it does transform under the anomalous symmetry. And we have only one coupling which transforms under this symmetry, and that means that this quotient is actually empty. Okay, so we don't have exactly marginal deformations for this theory. So that means that the gauging is marginally irrelevant. We start from zero coupling, and we cannot go out of this zero coupling. We are stuck to that point. Okay, so for general n, for SUN, SQCD with 3n flavors, the gauging is marginally irrelevant. Okay, so we don't have a conformal manifold. However, for n equals 3, something special happens. Okay? For n equals 3, we have additional operators which are marginal, and these are the baryons and the antibaryons. Okay? The operators of the following form: QIA, QBJ, QKC, which are the baryons, and the antibaryons, epsilon ijk, q tilde ai, q tilde jb, q tilde ck, are marginal. Okay, these are free fields, so they have R charge 2/3. So the R charge of this operator is 2. These are gauge invariant because they are baryons and antibaryons. So we have more more marginal deformations. And now the question is, which ones of them, or how many of them, are exactly marginal? Okay. So first of all, we need to understand what are the representations of these fields and correspondingly of their couplings. So we have 2 SU9 symmetries which rotate Qs and Q tildes. So the B's are in representation, 84-dimension representation of one of the SU9s and singlet of the other, and they are charged with plus sign under the baryonic symmetry and say with plus sign under the anomalous symmetry. The antibaryons are singlets under one of the SU9s and transform in 84-dimensional representation under the other, where this 84-dimensional representation is just 3-index antisymmetric representation of SU9. Okay, and then we have the corresponding couplings, which transform in the conjugate representations to this one. So the quotient we need to compute is the following. We have these couplings, lambda and lambda tilde, where lambdas couple to b's and lambda tildes couple to b tildes, and the gauge coupling under the same group that we had before. Okay, I will not write again. This is the anomalous symmetry, U1 baryon, and the 2 SU9s. Now this quotient turns out to be not empty. Okay, first of all, the problem we had before was only the gauge coupling was that it was the only thing which was charged under the anomalous symmetry. So we could not, the quotient was empty. But now, under anomalous symmetries, both these guys are charged with a, say, plus sign, and this is charged with a minus sign, or rather other way around, to be precise. So we can compute this quotient. If you remember your supersymmetry classes, these types of one way to compute these quotients is to form all the invariants under this global symmetry group using these elements of the set you are quotienting. Okay, so you just build all the possible powers and combinations of these couplings that will be invariant under this symmetry group. So since here we have something which is charged with plus and something which is charged with minus under some symmetry, we can form such invariants. In the same way, the same holds about baryonic symmetry. This coupling is charged minus, this coupling is charged plus, we can win this game of computing the quotient. So now the really interesting question is whether we can find the quotient under the non-abelian groups. Okay, so since I'm running out of time and I want to perform this computation slowly, maybe I better will start with this computation next time. So any questions about this? Yes, so let me stop here and take questions about the whole lecture.
So maybe I may ask a general question. At the very beginning, you mentioned that there is a technique that is this anomaly, which will help us to find which will help us to understand the RG flow.
Yes.
But here, indeed, you somehow connect this big function with this anomaly function, but it didn't seem quite the way that we use anomaly.
It's not the same. So there are two things. We will use anomalies in two ways. One way, again, this is the way which is which holds for non-supersymmetric theories, and this is the 't Hooft anomaly matching between the UV and the infrared. You just, if you have a certain statement, if you think you understand what is the physics in the infrared, you should check what are the anomalies, and the anomalies should match between the UV and the infrared. In supersymmetric theories, there is this additional thing that you have this U1, very special U1 symmetry, which is this U1R symmetry. And it interacts, through the supersymmetry algebra with your space-time symmetry. And in particular, it can tell you something about the beta functions, about the conformal anomalies, and so on. And you can use it to derive certain results. So in the second part of this talk, I was focusing on these arguments. Okay, these are different types of arguments. If you wish,
yeah, I mean, for the first argument, it seems it is more intuitive. That means if I have anomaly in the UV, then in the IR, this symmetry should still be feasible, should still act feasible on the low energy theory. Yes. But in the second argument, is there any relation with the previous one? It's always a completely different thing.
So philosophically, these are a little bit different arguments. So the 't Hooft anomaly matching is something of the following sort. You compute the anomaly polynomial here, you compute it here, and they should agree, right? Yes. So the other things that we have discussed using the R symmetry anomalies are actually somehow related to the vicinity of this point. So one thing, this was the last thing that we have discussed, how we know that a certain deformation is relevant or irrelevant or marginal in this locus. So it's just a question like where we go from this fixed point. And here, these 't Hooft anomalies helped us to understand that. So it's not that we deduce something about this fixed point. It deduced where we go from this fixed point. Okay.
Okay.
Another thing was this anomaly, anomaly maximization, A maximization, which told us what is the A and C anomalies, what are the A and C anomalies in the infrared if we know these are symmetry. And this uses the 't Hooft matching, anomaly matching argument, but it is more than that. It uses that and the structure of the superconformal group. Okay, how does it use the 't Hooft anomaly matching? Well, to perform this anomaly maximization, we needed to know the trace R and trace R cubed anomalies, and the trace U1 and trace U1 cubed anomalies for all the U1s that we have in our model. And we needed to identify them in the infrared. Okay, so we compute them in the UV, and we know that they are the same in the infrared by 't Hooft anomaly matching condition. But then on top of that, we introduce new piece of information that these anomalies, satisfy certain equalities and certain inequalities, and that allowed us to deduce what are the A and C anomalies in the infrared. Does this help?
Yeah.
Again, I want to stress that with N=1 supersymmetry, which is a minimal amount of supersymmetry, there are not too many very general tools that give us, certain information about the infrared starting from UV. So 't Hooft anomalies are the non-supersymmetric things. And then with supersymmetry, we have these several tools that I have discussed, and we will discuss next time one additional tool, which is very powerful. But there are not too many things that we can do. But still, the things that we can do are extremely powerful.
So any other questions? Okay, I guess the time is up. So if there's no further questions, let's thank Professor Schlomo Razamat again for the brilliant talk.